We're starting off our second of 3 chapters on equilibrium, and this chapter, chapter 16, focuses mostly on acids and bases. So let's go ahead and just get started. The first big topic we'll discuss in this chapter are conjugates, acid, and base pairs. It's probably not something you talked at all about last year, but let's go ahead and take a stab at it. The first example here we'll look at is having some nitrous acid, HNO2, plus some water. And we got the back and forth arrow thing, just like we had in the previous chapter. And then we produce some nitrite ion and some hydronium ion. This is the reaction. Again, it's going back and forth. And we're trying to figure out, looking at this, is which is the stronger acid. So one of the things we have to take a look and say, well, what is an acid? An acid is something, and we'll look at this again with some other definition-y things. An acid is something that donates a hydrogen atom. So if you look back at your previous chemistry course, whatever it was, there's actually 3 different ways you can look about defining an acid or a base. There's one scenario that says an acid is something that donates a hydrogen to water, and a base is something that donates a hydroxide to water. That is something called the Arrhenius acid-base definition. We're not going to use that. If you look at the beginning of on the front of the packet, the notes I would have handed out to you, or you have, we're going to use the Bronsted-Lowry definition, which is pretty much what I like to call follow the proton, or hydrogen. Acids donate hydrogens, and bases accept them. Pretty easy. So looking at these pairs here, we can take a look at the HNO2 and NO2. Clearly, it has lost a hydrogen. So on this side, this is acting as an acid because it has donated a hydrogen. I'm going to write that above. It's acting as an acid. Therefore, I don't really have an option. If you have an acid, you must have a base. So this is interesting. Water is acting as a base. That might blow your mind. I don't know, maybe not. So water can either act as an acid or a base. It's something called amphoteric. It can do either or. In this particular case, because it's acting with an acid, it's acting as a base. So therefore, it has to pick up the slack. But remember, this is an equilibrium, and we can look at both directions. So if I look at it from the other direction and pretend that these are my 2 reactants, who is donating a hydrogen? Well, clearly only one has the opportunity to act as a hydrogen donor, which would be this one, the hydronium. So on this side, it is acting as an acid, and this, of course, is accepting the hydrogen. No hydrogen, hydrogen. It's acting as a base on this side. But we typically like to distinguish between the right side and left side of the arrows. The things on the left side over here are going to be listed just as they are, acid and base. The ones on the right side, and typically we look at these as like the resulting species, the ones that are produced, we refer to these as conjugate bases and conjugate acids. So regardless, I could have wrote this exact same equation, flipped it. In other words, these guys are on the left and these are on the right. If I had done that, these would be bases and acids. These would be conjugates. So it just depends how it is presented to you. Clearly, this is the way it's given to me. I'm going to work with that. Our next step is to look at this and say, okay, well, which direction is favored? We are going to look specifically at our 2 acids, conjugate and the regular acid. If I look in your book, which is Appendix D, I can take a look at how these 2 guys behave. H3O positive, it has a value of 1 times 10 to -7. Its concentration in an aqueous solution, which means its ability to dissociate and act as an acid is this amount. That's what it would be present in. If I took HNO3 and put that in an aqueous solution, and the concentrations are always 1 molarity. Its ability to dissociate and act as an acid is going to be 4.5 times 10 to the 4. So its ability to dissociate and form ions is going to be this amount. So in regards to who is acting as a stronger acid, the larger value is acting as the stronger acid. So therefore, this is the stronger acid. So therefore, the equation is going to push in this direction. Now, one last thing as far as just, kind of matching these guys up, seeing like who does which pairing. This one's pretty straightforward. These two guys go together and these two guys go together. So as far as an acid base conjugate pair, this is kind of how these guys are going to line up. Okay, a couple more things we'll add into this video, or this little section here. Strong acids not found in solution. And there's 7 of them. And you may already know these, but we'll just list them off here. Hydrochloric acid, hydrobromic acid, just going down the line. Hydroiodic. These 3 are all like within the halogens group, all very strong acids. Notice hydrofluoric, which a lot of times we like to think should be on the list. It is not. That is a weak acid. These 3 halogen acids. The next 2 I like to refer to are both strong industrial acids, which are HNO3, nitric acid, and sulfuric acid. 2 very strong industrial acids. The other 2 are oxy acids, and they're chlorinated. Chlorate and perchloric. I say chlorate, excuse me, chloric and perchloric acid. These 2. So these 7 acids all act as very strong acids, and you will not find them, or actually when these go into solution, they will all go completely to products. So they will not form an equilibrium. They will all go completely to products. And the strong bases that we're going to look at here. So the strong bases not found in solution will be CH3 minus, H minus, kind of weird, and O2 minus. All of these species, if they were present in solution, they would immediately grab a hydrogen away from water, and what they would end up forming is OHs as a result. This would be the end result of that scenario. Okay, moving along. A couple examples to look at. We're just kind of make our way through here. So we're going to calculate hydrogen ion or hydroxide ion. If we have one, we can get the other one. Let's look at a scenario which is called auto-ionization, or I'll look at it a little differently. Water will somewhat break up, ionize, and form these 2 species, hydrogen ions and hydroxide ions. And putting this together, if we look at what we did in the previous chapter as far as making an equilibrium expression, we would say K is equal to products over reactants. So I would say H plus concentration, OH minus concentration, and then I'm not going to write H2O because it is a pure substance. It's not going to change concentration. So this is it. Now, this is a special K value, and I'm going to write down a little W here just to signify that as special. Now, based in a pure water solution, as far as what this will turn out to be, and it is the value for Kw, it is 1 times 10 to the negative 14. And if you sort of starts to look familiar to me, the value of the hydrogen ion concentration is 1 times 10 to the negative 7. And the hydroxide, therefore, is 1 times 10 to the negative 7 as well. Of course, we'll get there in a minute. So these two concentrations in a pure water solution are constants. All those values are constants. Okay, working back with what we have over here. Given this scenario, at 25 degrees Celsius, I have these two guys, which I've already kind of identified. Hydrogen ion concentration is equal to the hydroxide ion concentration, and they both are equal to 1 times 10 to the negative 7. Just to clarify that, when H plus times OH is equal to 1 times 10 to the negative 14. And again, Kw for water is equal to, every single time, the Ka concentration for the acid times the Kb concentration for the base. They must equal this. If I know one, I know the other, which is going to come in handy often. All right, before I finish this up, I'm kind of at the end of the time here. Let me go ahead and pause and we'll pick it up in the next video.